Hello everyone. In this part of our discussion on molecular spectroscopy, we are seeing the fundamentals of Raman spectroscopy. Raman spectroscopy makes use of the rotational and the vibrational motions of molecules, and we have seen in two previous discussions that the microwave spectroscopy and infrared spectroscopy both make use of rotational and vibrational molecular motions respectively. Here in the current discussion on Raman spectroscopy, we will be making use of such details presented there. So I think it is worth visiting those discussions too. And we have seen there the microwave and infrared spectroscopy make use of absorption of light by molecules, whereas Raman spectroscopy makes use of scattering of light. And so we start with scattering of light. Scattering is one of the consequences when light falls on a substance. The light can be absorbed, transmitted, reflected, or can be scattered in all the directions. And if the scattered radiation frequency and the incident radiation frequency are the same, that is called Raleigh scattering after Lord Rayleigh. And the cases where scattered radiation frequency differ from the incident radiation frequency are called Raman scattering after Sir C.V. Raman, who brought the 1930 Physics Nobel Prize to India. And Rayleigh scattering is elastic in nature in the sense that during the scattering the molecules are left in the same quantum state as before, whereas the Raman scattering is inelastic, that is, the light scattering leaves the molecules in different quantum states. And now let's see what does that mean. Molecules have got different electronic energy levels like the ground electronic state and the first and further excited electronic states. And we know that within each electronic state there are several vibrational states, and within each vibrational state there are several rotational states. And what happens during scattering is the molecule excites to a virtual excited state and immediately de-excite back to the original state, and that gives rise to scattering. Here you can see that the original state of the molecule is the zero vibrational quantum level, and after the excitation to the virtual state it de-excites or it comes down back to the same vibrational level. The molecule started from the ground vibrational level V equals 0, and after scattering it is now left at the same level V equals 0. That corresponds to the same frequency condition for both the incident and scattered radiation, that is Rayleigh scattering. And on the other hand, if the molecule excites from the ground vibrational level and it comes back to the first excited vibrational level, there is an energy difference between the incident and scattered radiations. So here the scattered radiation energy and the frequency will be lower than that of the incident radiation, and that corresponds to Stokes lines in the spectrum. And the reverse, that is the excitation from a vibrationally excited state and de-excitation to the ground vibrational state, this will give rise to a higher energy scattered radiation than the incident radiation, and such lines are called anti-Stokes lines. And the Stokes lines and anti-Stokes lines both correspond to the condition of Raman scattering, that is, the scattered radiation frequency differ from the incident radiation frequency. So the respective spectral lines will look like this. Here this line in the middle corresponds to Raleigh scattering, and the two on the left and right corresponds to Raman scattering, the one on the left being the Stokes line and the one on the right is anti-Stokes line. And now let's see a bit of the details. We have seen in the previous discussions that absorption of light, as in case of microwave and infrared spectroscopy, is associated with the varying molecular dipole. But scattering is not such an oscillating dipole phenomenon, but it is associated with a field-induced polarizability. That is, presence of electric field from the electromagnetic radiation induces some kind of polarization in the molecule. Here you've got your molecule, the electron densities are spherically distributed, and if you place the molecule in an electric field, like in case of exposure by electromagnetic radiation, the electric field associated with the electromagnetic radiation induces a distortion resulting in a kind of polarization within the molecule. And as the electric field strength increases, you can see that this polarization or this distortion is also increasing accordingly. This spatial charge separation under the electric field is called polarization, and the induced dipole moment during the polarization is directly proportional to the applied electric field strength, and here the constant alpha is called polarizability. Alpha, or the polarizability, says to what extent the molecule can be distorted or polarized in presence of the electric field. And polarizability may vary with direction of the electric field. That is, if you apply the electric field in this direction along the molecular axis, you can have distortion along this direction with an induced dipole moment in this direction. But if you apply the electric field in a direction perpendicular to the axis, you get the distortion also in this axis, and the dipole moment is oriented in this direction. That means the polarizability change according to the direction of the applied electric field, and that is called anisotropy in polarizability. And for a molecule to respond to Raman spectroscopy, it should possess an isotropic polarizability. That is, with the oscillating electric field component of the electromagnetic radiation, the polarizability of the molecule change, and that causes the inelastic scattering of light by the molecules. And let's now see the mathematical explanation for this. The induced dipole moment due to the exposure to the electric field is given by this expression. We know that the electric field component of the electromagnetic radiation varies with time, and likewise the polarizability also changes, and delta alpha is the rate of change of polarizability. And by using those two equations, we can write the induced dipole moment as product of these two. And after solving, we get an equation with three components inside like this. And let's now impose a condition that the change in polarizability alpha is 0. That is, the molecular polarizability is isotropic. There is no change in polarizability. Then the second and third terms of the equation disappears, and it will become like this. And this corresponds to the Raleigh scattering. And on the other hand, if delta alpha is non-zero, all the three terms of the equation become valid, and we can see that the first part of the equation contains the nu zero, that is the frequency of the incident radiation, and that corresponds to the Raleigh scattering, whereas the second and third parts, which is valid when there is a change in polarizability delta alpha. And you can see that in this second part of the equation, the frequency becomes slightly less than the incident frequency nu zero, and that corresponds to the Stokes line. And in the third part, the frequency becomes slightly higher than the incident frequency nu zero, and that corresponds to the anti-Stokes lines. So the first part of the equation represents the Raleigh scattering, and the second and third parts represents Raman scattering, and it explains Stokes and anti-Stokes lines separately. And therefore, it is obvious that for Raman scattering to occur, there should be a non-zero change in polarizability. That means the molecule should be anisotropic. And so we have our gross or global selection rule that for a molecule to be Raman active, it should have an anisotropic polarizability. Considering a spherical top molecule where the moments of inertia about the three coordinates are the same, the structure is so symmetric that the polarizability is isotropic, and hence such molecules will be Raman inactive. And coming to the specific selection rules, for vibrational Raman, the change in vibrational quantum number should be plus or minus 1, and the plus 1 corresponds to the Stokes line and minus 1 corresponds to the anti-Stokes line. And for rotational Raman, the change in rotational quantum number states either 0 or it should be plus or minus 2. Plus 2 corresponds to the Stokes line and minus 2 corresponds to the anti-Stokes lines. With that, let's now move on to rotational Raman spectroscopy. We have this from our previous discussion that the rotational energy of a molecule corresponding to the rotational quantum number J is given by Bj, J plus 1, where B is the rotational constant. And here is the specific selection rule. Correspondingly, for a transition from rotational level J to J plus 2, it is noted like this, that is, this representation says that the excitation occurs from the level J to J plus 2. So in this case, the calculations will lead to this expression that the difference in energy between the levels J and J plus 2 is B into 4J plus 6, where B is the rotational constant. And here are the different rotational energy levels, and let's now consider the transition from J equals 0 to J equal to 2 with a delta J value plus 2. That will give rise to an energy difference of 6B between the initial and the final energy levels. And corresponding to the delta J value minus 2, that is from J equals 2 to 0, you get the same energy difference 6B. And in the spectrum where you have got the scattering frequency plotted, you get a high intense Raleigh line corresponding to delta J 0, and to the left to the Raleigh line you get the Stokes line corresponding to energy 6B, and to the right you get anti-Stokes line with 6B units of energy. And likewise, the second possible transition is from J equal to 1 to J equal to 3, giving rise to the Stokes line, and 3 to 1 will give you the anti-Stokes line with an energy difference of 10B units, and that appear in the spectrum like this. And the next possibility is between levels J equals 2 and 4 with an energy difference of 14B, that will be seen in the spectrum. And the next possibility is 3 to 5 with an energy difference of 18B. Corresponding to this plus 2 delta J value, you get a Stokes line, and corresponding to minus 2, you get an anti-Stokes line on the right side. And it goes on. This is the pattern of rotational Raman spectrum, where the line in the middle is the Rayleigh line, the high intense line because it corresponds to the most probable transition, and on the left we have Stokes lines, and on the right we have got anti-Stokes line. The Stokes lines are more intense than the anti-Stokes lines. That is because for Stokes line, the molecule is in the lower energy level in the beginning, whereas for anti-Stokes line, the molecule is already in the higher energy level or in the excited rotational state. The probability that molecules are in the excited state is much less than the probability that molecules are in the ground state or a lower energy state. Therefore, this transition, the Stokes transitions, are more probable than the anti-Stokes transitions. Therefore, the Stokes lines are more intense than the anti-Stokes line. And we can extract some more information from this spectrum. Let's have a look on the spacing of these lines. The first Stokes line and the first anti-Stokes line are separated from the Rayleigh line in the middle by 6B units, whereas the adjacent Stokes lines are separated by 4B units, and similarly the adjacent anti-Stokes lines are separated by 4B units. So from a rotational Raman spectrum, you get this B values like this, and B value, the rotational constant, contains information on moment of inertia, bond length, atomic masses, etc., as we have seen in the previous discussion on microwave spectroscopy. And now let's move on to the vibrational Raman spectroscopy. The vibrational Raman spectrum is complicated by more additional factors, such as vibrational transitions are accompanied by rotational transition, because we know that within each vibrational level there are several rotational levels. So when the molecule excites from one vibrational level to next vibrational level, it can involve rotational transitions too. And the other complication is that vibrational motions influence the rotational motion. That is, the bond length and the rotational constant are affected during vibrational motion. Already we know that vibrational motion and rotational motion do not follow our standardized assumptions of rigid rotor or anharmonic oscillator. So all those factors bring in higher and higher degree of complexity in vibrational Raman spectra. So this makes the quantum mechanical selection rules to be more complex, and based on the molecular symmetry, the specific selection rules changes. For example, for a linear rotor, the specific selection rule is the change in vibrational quantum number by 1 unit and change in rotational quantum number by 0 or 2 units. Whereas for a symmetric rotor, the change in rotational quantum number should be 0 or by 1 unit. And more other considerations are also added for selection rules. Currently, we are not going into that detail. Instead, let's see how a rotational vibrational Raman spectrum or Ro-Vobrational Raman spectrum is originating. We know that the vibrational energy corresponding to the vibrational quantum number V is V plus half omega, where omega is the oscillation frequency. And Let's consider this particular set of selection rule, that is delta V is plus or minus 1, delta J is 0 or plus or minus 1 as valid for a symmetric rotor. Here are the two vibrational levels, V equals 0 and 1, and within each vibrational level there are several rotational levels. And consider the excitation from V equals 0 to V equal to 1, and within that we have got the possibility that delta J equal to 0. That means the excitation from J equal to 0 from the ground vibrational state to J equal to 0 in the first excited vibrational state. And likewise J equal to 1 to J equal to 1, 2 to 2, 3 to 3, 4 to 4, etc. All those transitions corresponding to delta J equal to 0 give rise to Q branch in the spectrum. Now let's consider this set of transitions, that is J equal to 1 to 0, 2 to 1, 3 to 2, 4 to 3, etc. That is delta J equals minus 1, and these transitions will result in P branch of the spectrum, and the reverse, that is delta J is plus 1 by excitation from J equal to 0 in the ground vibrational state to the J equal to 1 level in the first excited vibrational state, or J equal to 1 in the ground vibrational state to the J equal to 2 in the first excited vibration state. These transitions give rise to R branch in the spectrum. So this is how a rotational vibrational Raman spectrum look like, or a Ro-Vobrational Raman spectrum looks like. For example, the rotational vibrational Raman spectrum of hydrogen chloride consists of P and R branches. Here the Q branch is absent because delta J equal to 0 transitions are not permitted in case of hydrogen chloride. And now let's see the different vibrational modes in water molecule, and in that which are the Raman active motions. The first one, the symmetric stretching, is associated with a change in polarizability, hence this motion is Raman active. And the asymmetric stretching like this is associated again with a change in polarizability, hence the motion is Raman active. And the bending motion, the symmetric bending or scissoring, is associated with a change in polarizability, hence it is Raman active. So all the three modes of motion in water molecules are Raman active. And coming to the linear carbon dioxide molecule, we can see that the symmetric stretching is associated with a change in polarizability, hence it is Raman active, whereas the asymmetric stretching like this does not cause a change in polarizability, hence it is Raman inactive. And the two bending motions, the in-plane bending and the out-of-plane bending, are Raman inactive because there is no change in polarizability. So we can see that among the four different vibrational modes in carbon dioxide, only the symmetric stretching is Raman active, whereas the asymmetric stretching and the two bending modes of vibration are Raman inactive. And let's now compare the Raman and IR activities of carbon dioxide molecule, which is a centrosymmetric one. That means the molecule possesses a center of symmetry. So in that case, we see that the symmetric stretching is IR inactive and Raman active. The asymmetric stretching is IR active and Raman inactive, and the symmetric bending or the scissoring motion is IR active and Raman inactive. That means those vibrations which are IR active are Raman inactive, and the vibration which is IR inactive is Raman active. This is true for all the molecules possessing a center of symmetry. So we reach at the conclusion that for a centrosymmetric molecule, the IR active vibrations are Raman inactive and vice versa. This is called the rule of mutual exclusion. This helps us in molecular structural characterization that IR spectroscopy and Raman spectroscopy can complement each other for a stronger structural characterization. And now let's see how a Raman spectrometer looks like. Here it is. It consists of a laser source, and then the laser passes through the sample cell, and from the sample cell the scattered radiations are directed to the wavelength selector and then to the detector. From the detector, the data are collected and analyzed by the computer system to get the spectrum. This is the simplest schematic of how a Raman spectrometer is working. We have seen that Raman and IR are two complementary techniques, and Raman spectroscopy has got certain advantages over IR, that Raman scattering is very weak in case of water, whereas IR absorption is very strong. So water cannot be used as a solvent for IR spectroscopy, whereas for Raman spectroscopy, water can be used as a solvent. And as water can be used as a solvent, we can use the method for biological samples. And the instrumentation is less complicated, easy to handle, and no overlapping spectral bands are there. The spectral patterns are less complicated than IR, so it is easy to interpret also. And symmetric vibrations are observable, which are not observable under infrared absorption spectroscopy. That's all about the introductory Raman spectroscopy, and let's close for the time being, and in the next session we will meet with UV visible spectroscopy. Thank you.